Well, great. Hi, everyone. I'm Allie Tamburo. So this is my picture here. I work on the internal recruiting team at Citadel Securities. I sit in our headquarters, Miami, but I brought the sunshine with me to London this week. Yeah, and I guess caught the room on fire. Let's quickly just get to know the audience and people here, the group here. So quickly raise your hand if this is your first C++ meetup. Great, welcome. This is my second one in London. Raise your hand if you work in finance now. Whoa. Wow, this is more than I thought. So raise your hand if you think using C++ in finance is all about optimizing. Good, okay. My next question was raise your hand if you think it's hot in here. So we've addressed that. But let's get into a few panel questions I'll ask, and then definitely want to open it up at the end for your all questions. So first one here is, what drew you to working in financial markets as an engineer?
I can answer that. I was following the path of every normal engineer, and I was going to start working in security or encryption or something really cool. And a friend of mine suggested that I send my resume to a very large financial institution. And I thought, oh, these decrepit dinosaurs, all they do is COBOL and mainframes. And he told me, no, dude, you don't get it. These people, they have a ton of money, and they invested in really good technology. They do a lot of C++. And I was a bit hesitant, but honestly, I interviewed with them. I started working a week after, and I never regretted it. I had an enormous ton of resources, people that really knew their languages, and I'm talking very early C++. It was a great experience, and I never looked back.
How long ago was that?
That was 96, so pre-templates. In fact, we probably were one of the first shops to start using templates commercially in production trading systems, if not the first.
Slightly later than 1996, not by much, I should say, but apart from that, same story for me.
Nice.
Yeah.
What about you, Timur?
So unlike Juan and Carl, I'm actually very new to finance. I spent a decade of my career in the music production software, and particularly I was interested in kind of the low latency, kind of lock-free audio processing stuff. And I have been giving talks about low latency C++ for a good decade now. And then I noticed that something very interesting was happening. All of these finance people started coming to my talks, and they started actually talking about really interesting things. Oh yeah, we have something similar going on, but it's actually different. And I realized that they were doing really interesting technology there. So I got really curious, and it turns out there's actually a lot of overlap because finance cares even more about low latency than audio processing does. And some of the kind of constraints and the ways to solve problems are actually very similar. So there's some transferable skills. But some of them are also very different in very interesting ways. So I found that for me, it's just a very cool way to learn more about this kind of low latency space and to work with a really cool tech stack. And it's been a lot of fun. So yeah.
I got to say, the very first C++ team I was associated with, I was writing C code in the cubicle next door, but it was for that team. They didn't let me do C++ yet. This was 1994, and I was just still learning it. But that was a derivatives trading system, so I learned that derivatives are about more than calculus at a major Canadian bank, which is now known as TD instead of Toronto Dominion. It's still around. Then I took a detour into big tech, so it's coming home in a way. And boy, have things changed in 25 years.
Nice.
30.
Approaching
oh my
30. Yeah, maybe a little more.
Yeah. Moving on.
Okay, more C++ specific. Where does C++ matter most in your systems, and why is it the right tool for those problems?
So I guess it matters. Well, it matters in a lot of different parts of the stack, and that's kind of its superpower, I guess. Yes, Python has been in the really we need to do something quickly and prototype things and give it to users who are not necessarily very experienced in doing things. with technology, but C++ is everywhere else, right? And the reason for that is both all of the things that we have heard about today, but also the fact that we can get people who understand all those things that need to be understood when we look for C++ programmers, right? Like, tech is fundamentally maintained by people. You need the people who understand the whole stack to maintain the stack. C++ is the language that has that community.
Okay, leaving C++26 aside, which modern C++ features have had the biggest impact in finance for you?
Yeah, C++11 was huge. Move semantics, const expression, all of that good stuff. Anything around memory or moving things to compile time, just absolute game changer. In fact, I remember getting my hands on C++11 compilers later than 2011, but we'll put that aside for a second. Yeah, just quality of my life just shot up.
Stud atomic. Enough said.
So I would say it's probably the boring answer, but like templates and const expr. And I know that const expr is not exactly modern, you could say, because we got it in CSS 11, but actually every single subsequent standard added more stuff, like 14, 17, 20, 23, 26. In each and every one of them, we got more cool things that we can now do at compile time. And we use that very heavily. And that's kind of like, I would say, the most impactful, like kind of day-to-day code thing.
I'll just make the observation that most of the things just mentioned were C++11. Still, C++'s most impactful release to date. That's the hurdle we want to clear in 26 for the first time in that many years.
I always want to point out polymorphic lambdas, but that's a detail.
That was 14.
Yeah, that's why.
But you got
Yes.
lambdas in 11.
Yes.
You were happy, right?
Yes.
Okay, good.
Yes. Well, now C++26, which features do you think will have the biggest impact?
Reflection.
There we go.
Sorry.
We're excited.
Come on, Gasper,
Anyone
you love
else?
Citadel Securities.
Okay,
You
yes.
just talked about it.
I gave a full talk about it. Yes, but the problem is that execution is going to have a big impact in C++ 26 plus, because somebody needs to write all the libraries.
Right. I think that reflection is it's a new language. At the same time, stud execution is going to fundamentally change the way people write their code today. So both are complementary.
So I agree, reflection and execution, definitely number 1 and 2, but solid third place, I would say contract assertion. Obviously, I'm a bit biased. No, but let me elaborate just a little bit. So we now, for the first time, have a way of expressing in code in a way that the machine understands when we, as the designer of the code, the human, consider our program to be executing correctly at scale in a portable way. Right? And that is big. That is big for finance, and it's absolutely no coincidence that most of the development of that feature came from finance. That's not a coincidence.
Cool. Exciting stuff ahead. What about, do you see C++ in the next 5-10 years being displaced by another language?
It's hard to imagine because C++ has a durable, enduring value proposition that only C and Rust also have, which is close to the metal. We just talked about that, getting the most performance per watt. And C++ is growing faster. We just added more features in the past year than there are Rust developers on the planet. More developers, I mean, more programmers, more C++ developers. Not more features. I know. That's gonna hit the internet. More developers in the past year than Rust developers on the planet. And Rust is going gangbusters. It's a great language. I like Rust. But C++ has an ecosystem that is unparalleled. It is also moving forward, and it's accelerating fast. I think Python is a wonderful language. I hang out with Guido. He's a great guy. It does things C++ will never do, and vice versa. They're complementary. So I don't think it's a matter of taking over. I think that C++ has a long, enduring future. Even C has been growing because of the demand for access to the hardware.
Nice. Okay. I'm going to stop asking questions because we want to get to your all's questions. So if anyone has a question, we have a mic. And we can start over there with Matthias. Oh, Matthias in the corner. I called him out.
Oh, here. Do you want to?
So I have a question about what's it called, the sender receivers or execution. Do you feel that this could ever become like the low latency path? Because in finance, if you really care about low latency, you're using something like EFVI, DPDK, completely different from this kind of complex template-heavy system. But do you feel like the two could merge together?
It is very much QoI. It is possible to implement this form of DSL. Yes, it's possible, but somebody's got to do it, right? Like, it is not a small amount of work, and it's extremely high skill. So, do we have that in-house? Perhaps, almost. Would I like to see that? Yes. I think that the paradigm itself, it's effectively, like the low level of it is effectively based on the proactor model, which is extremely good to scale, right? Because all of your stuff is already ready to run by the time you get the signal. It's not a reactor model where you sometimes need to do extra work to react to the signal. So it is incredibly well suited for the low latency path if implemented correctly. That's a big if, though. It is a very load-bearing if. So yeah, if you know, like, it's possible somebody's going to do the work, and then it will. Or if nobody does the work, then it absolutely won't.
You're going to have to wait for me. Ooh, we might need to pass it.
Yeah. Pass it back.
Could you please pass this? Thank you.
Hello. Some of you said that it's time to start expressing the intent and not just how to do it, but what to do it. Can you tell a little bit about the process of how that intent gets expressed in the standard, where it's available in a stabler form, and what are some of the challenges that get in the way of making that intent available to us?
I think a good example is ranges. In ranges, you start, like, for lack of a better term, pipelining your transformations. If you want to extract the values out of a map, you no longer need to iterate and get that second. You directly just say, all right, give me the values. And that's a linear transformation, and it's lazy. You don't pay any cost for it. And then you start composing your algorithms based on that. So that is how the standard takes care of it for you. But of course, you are the person that needs to write the code. You're the final end user. So the standard will provide you with the tools, but you need to put the means of production, which are your hands and your intellect.
Was the question about, in general, what are examples of features in C++ that let you express intent directly? Or was it more about student execution?
I just meant that when somebody has an idea on how to express an intent, like the idea of ranges or idea of concepts came along, idea of deducing this came along to replace CRTP, how did it make it way, like how long it took, and what were the bottlenecks that happened that took it long to get to us, and us using to use Fine or things like that for such a long time?
Oh,
I'll take a quick path to that. So any standards proposal does take some years. It's not a few weeks or a few months kind of process. The most successful ones I've seen, and I'll just go back to range 4. I mean, that's a poster child simple example that we use every day, is people notice what people did without it. They wrote a naked for loop that incremented once, and you hope you didn't, and you learned the pitfalls of, Did I accidentally increment extra time in the body so I'm skipping elements or not? And was that on purpose or not? Wouldn't it be nice if I could just say what I mean? Look, other languages have this too. There's prior art we can refer to, not just imitative, but because there's prior art, that's information. So to see what people are doing by hand and saying, here are common patterns, we want to be able to express that directly. Lambdas are another example. People were writing functors for a long time by hand. A lambda gives you notation for saying, take this piece of code and pass it around. So maybe those are two examples, but it takes years because you have to learn from the usage patterns and then generalize to see, well, what is the missing abstraction here?
Hi. I have a question since we have people who have been in finance for a while. I heard, and I don't do low latency finance, that templates is one of the, like C++ finance is one of the heaviest users of templates. And I also heard that at some point people read modern C++ design and took it seriously. And so the question is, did anybody see that and like wrote those like factory patterns and all of that stuff for production usage? Have you seen? Okay, thank you.
I haven't seen that, but I have seen it avoided. I remember a year ago, I could anonymize this. Let's just say a new library written, which one of the observations was, gee whiz, this is slowing down compile times. Why? Because it's using Andre style. Template meta program, policy-based design, so that you're not passing concrete types most of the time, that every user and every supplier most of the time needs to be a template. And it becomes viral because there is not just a shared pointer, there's a shared pointer with these options. It wasn't shared pointer, it was trade related. And so that very quickly got changed to be concrete types and to not be policy-based design. So I haven't actually seen an example of that myself, but I saw an example of it being avoided on purpose because it was immediately noticed the impact on compile times. You guys who've been here longer would have more or less to say.
I completely agree with you.
I would say that it can definitely vary from company to company, and it can vary from team to team within a company as well. So if you can think it, someone's probably tried it. Maybe they've stuck with it, or maybe they've decided to try again. But yeah.
I guess I can speak to that a little bit more. As the frequent perpetrator of horrible template crimes. Basically, you start with templates. It gets too horrible. And by that time, you've mostly figured out what you're doing, so you make it not horrible by making things that don't need to be flexible, concrete, right? But without templates, you would have never gotten there because prototyping is too expensive, right? So it's another tool on a journey to get to good code, right? It's just all happens to run at compile time.
Okay, I'd like to ask about the features from Rust because I love both Rust and C++, and I really like to see two things in, C++. And first thing is like better error and exception handling because they're so conflicted. We have the exceptions in C++. We also have the standard expected, right? And in Rust, you have the also the result type. We can have the either some result or you have like an error type, right? So super simple to propagate, and also like a strongly typed. You cannot you need to do like some explicit conversion. Yeah, so it's very useful for our data platform. When and also the other thing is the better async programming, because when for our use case when have the do a lot of data processing, you need both things. So the first is async, and second thing is the error propagation. Yeah, so do you have anything on the horizon to bridge the gap between C++ and Rust for those two features? Thank you.
Didn't you have a paper about that, Herb?
Yes, I did. I was gesturing this direction. So my short answer is yes, you're right. There's more than one way to report errors in C++. It seems to be working, and Rust does it with a unified system. So does Go.
But also stud execution adds another one. So we have a completely separate forward error propagation channel in sender receiver because that is what you need if you want to do async. So it does interoperate with exceptions because you can make coroutines part of sender receiver, and then forward propagated exceptions just get thrown out of your await statements and things like that.
But can I take something that you asked and throw it at the state execution people? When you look at Rust, the feature I would adore and most like to see in C++ from Rust is not result. I mean, we have that library. That's fine, but it's not wrong. It just doesn't interest me as much. What interests me is fearless concurrency. Race-free by construction, which no major programming language has. Java doesn't have it, C# doesn't have it. But somebody was just showing some slides about that.
It does work if you don't do dumb things, but well, the thing is, dumb things in this new way are actually quite difficult to express. You have to go out of your way to do dumb things, which is a new thing in C++.
And I think the point you were making is because it's structured concurrency. State execution is all about letting you express, and you made this point as well, Juan, was structured concurrency, which is the special sauce that lets Rust get those guarantees. So it's no surprise that we start to see some of those benefits for concurrency safety as well. And that I find interesting and exciting. Because if anything makes Rust unique, it's the fearless concurrency part that distinguishes it from all languages, all major languages.
My question is, in like large production like code bases, do concepts meaningfully reduce like error rates, or do they mainly improve like compile time errors, diagnostics?
I guess I should speak to that because I use concepts probably the most out of this, well, realistically out of most of the company. Yes, but not the way you think. So concepts make it a lot more obvious what you're trying to say, because instead of insert token spew here, you have sortable, which is kind of nice. The other thing that they do is they make it really easy to make horrible overload sets, because people reach for them too often. Concepts are an unexpectedly sharp tool. And a lot of the time, what you actually want to do is instead of putting a concept into the function declaration and saying, I take sortable things, you want to say, I take anything, and then do static assert sortable. Because you didn't actually mean to overload. Again, you used concepts, but not where they were touted to be useful as in function interfaces. You don't always want Sphene. Like, Sphene is no longer Sphene, but it still causes all of the same problems, just with a nicer syntax. So again, it's a sharp tool. You got to know when to use it and when to not.
The question there in the back.
I was trying to give this side a shot.
Good evening, gentlemen. It's a pleasure to see so many illustrious people on the panel tonight. This is a bit more of a chatty question and kind of opinion, really, more than anything. But I've been doing C++ for longer than I care to remember, all the way back to '98. And I remember quite a long period when I was kind of in despair about the language a bit, really, because it kind of seemed to be falling into the doldrums and nothing much seemed to be happening. And then suddenly C++ 11 and 14 and everything that followed kind of exploded. And I just wondered what the panel thought about what changed in the standards world to push all that forward. And that's probably mostly for Herb, although anybody that has an opinion, love to hear it.
Bronick is making because it's about the train model. And I was not the only person to push for it, but it took me a couple of years to convince enough people of the committee, but I'm very glad that they let themselves be convinced to not do feature-based releases, but to do time-based releases and ship every 3 years. I actually asked for every 2 years, and the committee said, no, that's a bridge too far. We shall ship every 3 years. And I said, thank you. because it makes things more predictable for users. People wondered whether we were going to ship a second standard ever again. We were pretty hopeful, but even some of us started to wonder, because shipping is a feature, right? And so it also made it more predictable for tools vendors. Even for C++ OX, where X is hex, you know, all the jokes, because it was delayed, it still took several years for implementations to conform to the standard and for it to be shipped. And since 14 and onward, it has been quite normal to see a complete conforming implementation modulo bugs the same year the standard shipped. That never happened before, but it was because of predictable releases. So the community, but also the vendors knew that what to expect and that there would be an X and when it would be. So I think that made a big difference.
Okay, thank you.
And thanks to the whole committee for working to make that happen, because that was a whole load of work every time to stay true to that and to actually make it so every 3 years for 1, 2, 3, 4, 5 cycles now. The shipped on time.
The amount of work you do is terrifying, I'm not going to lie. Okay. Who's next?
Hi. I have roughly 3 questions around senders receivers. I originally only had 2, and then Gasper brought up coroutines, right? So the first one is about the scale of senders receivers, because all the examples we've ever seen were quite trivial, if I can be honest, right? And they were mostly just fetching web pages, small servers and stuff like that. And I work in games, and like I try to implement modern C++ features into my hobby project or in work and stuff like that. And with games being really, really large, right? We have multiple systems, like 10, 20 plus systems, trying to make the game work. I don't see senders, receivers working, or rather I haven't seen an example of that scale to let me convince my fellow game developers that, hey, we should jump in on this, right? And then the second question around compile times, I don't know if you guys heard of Matteo Ropert. He had, sorry? Yeah, he had a blog post on LinkedIn the other day, and he had it on Reddit as well, where he was trying to use senders receivers in his toy project, right? And I think a simple example of rendering a cube added 5 seconds to his compile time. And that's like a very simple example, right? So I was just thinking, what if we have like a full-blown game, like, you know, whatever game that's popular these days, like Counter-Strike or something like that, right? How long is that going to take? Because like the game I work on at work, a full build takes at least half an hour, right? And lastly, about coroutines, I'm not sure if you guys have seen Vinny Falco's paper on coroutines and still execution, how both of them kind of contradict with one another, because coroutines have semantic transfer, whilst senders receivers don't, and you know, trying to retrofit state tasks to, or rather senders receivers to, you know, you're kind of basically what he's trying to say is like he feels the community is trying to push semantic transfer into senders receivers. I don't know if you have any comments on that, but to me it seems like a valid concern.
I think my answer is going to be shorter than your questions. Okay, so let's start with, does it scale to large programs? Which is the first 2 questions combined, really, because large programs also have long compile times, and so I'll take them together. The answer is yes. I have done it. Was it easy? Not with my initial library, no. And I don't think that there is an open source library out there that can achieve compile times that we've got. It took me 2 weeks over Christmas in a hut in Scotland. Literally, like me and my wife went to Aviemore, and I coded all evenings to figure out how the hell to do a complete CPS transform in templates while type erasing literally everything. It is not trivial. But once you've done it, the compile times drop to 3% of what they were. Right? And stopped scaling quadratically. They scaled linearly from then on. So you got, like, it's all QOI, and it's not there. Right? No open source sender receiver version has the QOI that you need in order to do, industrial scale projects right now. So that answers the first two. Like, yes, Mathieu couldn't do it because he doesn't have a library that would support that kind of thing. With regards to coroutines, they have their own problems and they have their own strengths. We passed them for a reason. They're really good for some things. Sender-receiver gives you guaranteed colocality of data. It gives you hard real-time guarantees that without a lot of other work, that Vinny has also done, by the way. Like, he did a lot of work. It's very difficult to get hard real-time guarantees with coroutines, right? Our implementation has them. Was it easy? Hell no. So again, like it's basically like, yes, we have the raw tools, we have the APIs that are published, and then somebody needs to sit down and do an actual industrial strength implementation, and then it'll work, which is the same caveat I gave to Matthias.
Okay. Let's do one more, and then let's cool down with some drinks in the next room.
Oh, I should say that libunifx is pretty good, but it's not optimized for compile times.
Hi. Sorry if I spoil this conference with AI. It wasn't mentioned yet.
How we might escape with no
It has been
AI.
nice until this point. But in the context of the new C++ developers, which is very pleasant to hear, obviously, and many of them are presumably using AI, what are your views on potential of AI and lack of sort of need to have the same cognitive abilities that the old C++ developers used to have in order to call themselves the C++ developer? It used to be a lot harder, and I think we've done great making it easier, but I've seen examples of junior devs throwing nasty compiler errors at Claude Code because they didn't have time or desire to understand, and once it works, they don't care. Probably captured by the stats as C++ developers, but maybe shouldn't have. So the question is, do you use it in your company, and what are your views on the longer term AI usage? Thank you, and sorry for bringing AI into this. It was a nice conference so far.
I'll give a one-sentence answer, and then these folks will give more. AI is absolutely transformative, but don't drink the Kool-Aid and don't believe all the hype. This is like we still have a lot of human ingenuity is still needed for so much new stuff that we're able to do, but we'll be more effective doing it because of that. But yes, can people do terrible things with a new tool? Yes, as Bjorn likes to say, every new tool gets overused. But there may be more specific takes on it.
I don't want to get into giving weird examples or really, really fancy things that you can do with AI. I'm just going to give you an analogy. People used to diss about those weird guys that use debuggers, because who needs a debugger? And it would be completely unrealistic to think that today you can live as a C++ developer without ever touching a debugger. It's just a tool. And AI gives you the means of dedicating your brain cells to what really matter. You can tell the AI, look, just generate unit tests for this until you die, and it will do it. Or documentation, whatever. And you can really earn your money, like doing what really matters is what's really fun, which is real hardcore C++, which is what we all like.
Yeah, I don't see the need for people who really understand the language and the architecture and all of that goes into that, into writing like industrial strength software. I don't see the need for that going away anytime soon or maybe ever.
If I can. So AI fundamentally shifted the cost landscape of things we do, right? It fundamentally made some things extremely, extremely cheap, and we're not even sure which ones. Thank you, Maxime, for that observation. The surprising thing is more that because a lot of stuff got extremely cheap, right? Like, I don't know, banally saying, writing good commit messages. Really cheap now. Great. Writing all the test cases as opposed to the important ones. Really cheap now. Refactoring 100,000 lines of code from one API to the other where they sort of match. Actually really cheap. Like a few days of work and watching an AI do it on the side while you do something else. Like surprisingly cheap. But then you have other work that just didn't get any cheaper at all. In fact, it got more expensive because in comparison to the other work that we have to do, it is now more difficult to argue that you should do it. Right? Like, no, it's just a fact. So tools shift the cost landscape of engineering, and this is a tool that we haven't really figured out yet of exactly how it shifted it, right? So learning how to use it effectively, yes. Learning how it fits into your engineering organization, a slightly different question. But pay attention to it.
I find it particularly useful at reading the code and telling me what it's doing. Because that takes a long time sometimes, you know.
Yeah,
It's
so
game changer.
yeah, as somebody who's new to this entire industry, like I have actually, the last few years, I wasn't into jobs where I like look at code every day or production code. And I remember from like, it used to be that if you look at a big code base in a new industry, like that was quite daunting. And now it's so much faster. You just select, you know, a piece of code. What does this do? And you actually get really, really reasonable answers. So that's transformative, but that doesn't change the fact that I still have to conceptually understand what's going on. And I don't think that's going away. I just don't have to sift through lots of stuff manually to get there, and that's really good.
AI is only as good as the model, and you're only as good as your intellect. So that's a difference.
Okay. Well, let's head over there to that room. Hopefully it's cooler over there. There'll be drinks, food. Thank you.